Hello everyone and welcome back. In this video I am going to talk about improper integrals. Spoilers alert, this is the most fun type of integrals that you will ever face, at least from my own perspective. So let's get started. We are going to define and go over the basic concepts to understand how it goes, and then without further ado we will jump straight into the example. So let's do like the theoretical part really quick. So I am going to show you. So let's say that f is continuous on an interval of a comma infinity. So let's say that we've got this expression. So you may be wondering how we are going to express this like an integral. Well, it's not that hard actually. It's important to make use of our limits though. So this would be represented as the integral from a all the way to infinity, and of course we've got our f of x dx. So as you can see, the only thing, well, basically that is different comparing these type of integrals with the previous ones is that we are including an infinity in our definite integral. So from that point we start making use of our limits. So limit, and then we are going to give a demi-variable, which in this case will be t. To put it to we could have put any variable really. As I was saying, it's just a dummy variable. So as t approaches infinity, which is of course this side, and then we've got the integral of, then we've got our a here, which is this point right there. Then we put our t, we just do a simple substitution, and then we put our f of x dx. So that's how we can express the entire graph that we are looking at right now. So now let's say that we've got f continuous, but now this time it will be a little different since it's a different interval. It's from minus infinity all the way to b. So let's see. So right here we've got this is approaching minus infinity. So I am going to put this once again as an integral. So integral minus infinity all the way to b, of f of x dx. So now, once again, we are going to put this in terms of a limit. So limit, and then we are going to use a demi-variable. We can use anything. I am pointing this out. Sorry for being redundant, but I am going to put like x. No, x is too confusing. You should choose another variable other than y and x to avoid confusion. But you could have put like, I don't know, like x sub 1 or something like that. But there are many letters in the alphabet really. So let's put q that approaches minus infinity, and then we put q right here, and then we put b right there, and then we put f of x we're a little cramped right here, so, but it's f of x dx right there. It's as simple as that. So, lastly, but not least, of course, we're going to express a more difficult integral. So again, f is continuous, but now the interval is from minus infinity all the way to infinity. So how that looks? Let's check it out. Yeah, okay. So in my graph, it looks like a funny hat, but I can assure you it's not. So let's put this as an integral. So once again, we are doing almost the same thing, except that we are changing, of course, our definite integral. So it's the integral from minus infinity to infinity dx. So guess what? We're going to express this as a limit once again. So we are going to give a demi-variable. So let's put a different one. Let's be creative. We are going to put r to go from to minus infinity. Now we put, and then the demi-variable right there. And then we have the c point right here. And then we put f of x, and we are being consistent, dx. Okay, but there is a second part of this, which, since again we are running out of space, I've just rewrote it right here. It's again a little cramped, but it helps you visualize what's going on. So this second part, of course, like corresponds to, it's like c that approaches infinity. So it's this part. So we are using the demi-variable z to make it evident. And then on the other hand, we've got like our r that you've just seen right there and down at the bottom, that it's approaching minus infinity, so all this way. So that's basically it. That's basically what you need to take into consideration. But I am going to define certain things. So if the entire limit approaches towards a finite number, so let's say that it gets like hits the x-axis and it approaches, let's say, 0 right there, like y equal to 0, that means that it converges. Otherwise, if our entire limit approaches either infinity or minus infinity, we say that our limit diverges. So finite number means that it converges. So make sure to define these two things pretty well. You don't want to mess your entire thing up because of that. So we are going to get started with the problems in question. So the problem reads, find the integral from 1 to infinity of 3x squared plus 1 everything over x cubed plus x dx. Okay? So the first step, I mean, you can definitely express this as a limit. That's what we saw in the previous examples. So don't forget, let's give the demi-variable. So let's say we can give it s to be our demi-variable. So it's s that approaches infinity, and then we just simply substitute, okay, from 1 to s, and then we just stick to the rest. Plus x dx. So now what we got to do is to work the integral out, which is of course maybe the nitty-gritty of the problem. So I am going to pull it off right here. So we've got I would recommend treating this definite integral as an indefinite integral and just do like all the math and stuff, and then you can put the limits and put the bounds into the expression that you end up with, x cubed plus x dx. So now you need to be very careful at this stage and think about the method that you are going to apply right here. So this one, I would say that it's not so evident to see, but again, if you think outside of the box, you will notice that the numerator is the derivative of the denominator. So that tells you that you can do a u substitution. So our u is going to be x cubed plus x, and our du will be 3x squared plus 1 dx. So yeah, it wasn't too bad. It was fairly easy. And now what you get to do, of course, is doing the substitution. So you can do the substitution really quick. So you put the du right here, and then you put the u at the bottom, and then you just get to integrate this, which is ln absolute value of u. And is the problem over? Not. No, not at all. We are right in the middle, I would say. So now we can put our bounds. So it's as we saw from 1 to, I think we used s, right? So to s. So now we are going to express this as the limit. We are going to be consistent with our limit, which is, okay, so it's s as it approaches infinity. So we are just being consistent. I am going to jump straight into the next step, which is applying the fundamental theorem of calculus, which is natural logarithm absolute value of s minus ln absolute value of 1. And then what we've got to do here, don't forget that the limit applies for the entire expression. So if we start plugging stuff in, like for example the infinity right there, we know that natural logarithm of infinity is infinity. And I will, maybe it's a little bit redundant, but I am going to demonstrate why. So natural logarithm is logarithm base e of x of e to to the x equals x. So what we do when we apply logarithms, we are basically taking e, raising it to the result, and we get what it's right here. So we are essentially doing the same thing. So as you can see, in order to have infinity as a result, we need to elevate our e to infinity. So that's just infinity, and we don't even care what ln of 1 is. But just for the record, it's 0. So our entire integral is divergent because it approaches infinity. So you just need to state that really clear. So it's divergent, and you are done with the problem. All right, so now let's solve a different one. It's essentially the same, but different bounds. So here we have the integral from minus infinity to 0 of dx and everything over to minus x, everything raised to the 1/3. So now this is, I think, even clearer. I mean, we can simply do once again a u substitution, so that our u will be 2 minus x, and our du will be minus dx. Are we clear so far? So don't forget. I mean, well, you can. It doesn't matter. I mean, you can start by doing the substitution and then put it in terms of limits, or you can do like whatever, as long as you follow the steps. So we are going to give a demi-variable again. So let's say that it's r. So as r approaches minus infinity, we are going to substitute our minus infinity for r, and we are going to put our 0 here, and we are going to put our dx here. So 2 minus x, and everything raised to the 1/3. Now we are going to make use of our substitution, and we are going to, of course, start operating. So now we have the following expression. We can simply just pull the sign off. I am going to put the u to the 1/3 since it's in the denominator. I can rewrite it as u to the minus 1/3, and then just a matter of, so in order to have 1/3, we need to subtract minus 1 from another number, which you can, if it's not clear to you, you can put like an equality right here. So in order to have minus 1/3, you would need 1 minus 1/3. So you can express the 1 as 3/3, and then you just simply operate. So that means that it's 2/3. And that's what you get to put right here as the exponent, as the power. So 2/3. And we, of course, once again, we put everything over 2/3. And that's basically what we've got. But don't forget, we are just treating as an indefinite integral. That does not mean that it's an indefinite integral. So I am going to do the substitution in question. So I am going to get back to the variable. So okay, so it's minus, and it's 2 minus x, 2 minus x, everything raised to the 2/3, and everything over 2/3. Let's make sure everything is just fine, and the limit is, and the bounds are from r to infinity to 0. So we are going to rewrite that as limit as r approaches minus infinity, and it's from r to 0. Well, now since we've just found it, we have to express it just like this. So our expression, so our minus 2 minus x, everything raised to the 2/3, and everything over 2/3 by 2/3, and then we just simply put our r right here, and then our 0 right there. So yeah, I mean, it's, I would say, a messy expression, to be honest, to deal with. The good thing is that you are just going to plug in 0, and then the other expression is simply infinity. And since chances are that whatever you get here by plugging in 0 will be totally meaningless, because if the r turns out to be an infinity expression, the answer will solely be infinity, and that's it. So I would put a minus sign right here, since at the time of applying the fundamental theorem of calculus, we would be subtracting this. So I would put a minus sign right there, and I am doing like straight to the substitution. So this is our expression. Now we just get to, well, the minus sign will multiply the minus sign, so it's plus, and this entire expression. Don't forget that since we've got the limit as r that approaches minus infinity, this is going to be minus infinity, and then everything raised to the 2/3, and then everything over 2/3. And of course, if you just raised to the 2/3, so our entire expression is going to be simply minus infinity. So again, we can once again state that it's divergent. So I think that's everything that I've got for you today. I wanted to cover one more example, but I guess that I will leave it to you guys for later. So next time I will solve this integral. So if you want, you can try and see where you get, and it's just a matter of applying the concepts that I just covered, like at the very beginning. Just a matter of splitting this off and then just solving the entire expression. So thank you so much, and I will see you soon.